and there is some voltage between those two terminals. So we have the current, let's put I, and voltage, let's put V. Now for circuit theory, the definition of this object is by relating voltage and current on the terminals. And this relation is voltage is minus inductance times time derivative of current, that is di over dt. Please note minus. So the voltage and current in this picture have opposite directions. That's the circuit theory definition of an inductance. Now, we have defined, using a static definition, that the inductance is a ratio between flux and the current that has created it. Those two definitions use different values to get the definition, but anyway, the resulting value of inductance is the same. This is called static definition. This is called the dynamic definition. And we have a third one, which is based on energy. I will, just for the sake of having everything at one place, I will put it down here, but we will discuss it a bit later. This third definition says that the energy contained in the magnetic field of an inductor is equivalent to 1/2 of the product of inductance and the square of the current. Now, this is fully true for the assumptions we have made at the beginning, that we are discussing linear isotropic stationary media. The inductance in all those cases is the same inductance, just we have different views on that. So once we obtain an inductance from one of those definitions, we can use it for other purposes. For circuit theory, where voltage and current is important, for any application where the stored energy is important, and of course for flux and current definition, which is called static. So this is the static definition, dynamic definition, and energetic definition. All of those definitions refer to the same property of a coil or a conductor, which is called inductance. Now, to make things a little bit more complicated, this is very nice, but if this was the only inductance that existed, there would be no TV broadcasting, there would be no transformers, because there is another important and interesting topic, and that is self-inductance. So this is a self-inductance and mutual inductance. Self-inductance depicts the behavior of a two-terminal device, and a mutual inductance depicts the behavior of a device with more terminals. Most typically, let us have a wire, say a coil, in which the current I1 flows in this direction. This coil would create a magnetic field. The ratio between the flux and the current would establish self-inductance of this conductor. But the magnetic field is not restricted only to inside of this conductor. In fact, it decays with the distance, but still we have some magnetic field at any distance. What if there is another conductor and this conductor is positioned so that some part of the magnetic field created by the first current flows through the second conductor, let's say through the coil, and then we give birth to something which is called mutual inductance. We can define it again in several manners. First, of course, we can use a static definition which will be expressed in the term of magnetic flux and current. But now we have to be careful which magnetic flux and which current. A mutual inductance is denoted by M. The unit again is Henry. But now we have in the ratio the magnetic flux phi to 1, which is the flux which flows through the second conductor loop, but is caused by the first conductor current. So this current causes this flux. So there is a lot of flux created by this current, but only a part of that falls into the loop on the second conductor. And this flux that flows here and is caused by the current over here is the important one. Now, this flux should be divided by the current that caused it. So, divided by current 1. And for the sake of simplicity, we still use linear homogeneous isotropic media so that the inductance, mutual inductance from this conductor to this conductor and the other from this conductor to this conductor must be identical. Then we have this ratio established as mutual inductance of those two conductors. I will make an illustration a little bit later on calculating a simple case, but in order to use also the circuit theory definition, in circuit theory we can write down that the voltage in the second conductor that is induced by the change of current in the first conductor could be, depending on the orientation of those two coils, M di1 over dt. So the voltage in the second conductor, voltage 2, is proportional to mutual inductance and time derivative of current in the first conductor. This is again a kind of definition of the same quantity, mutual inductance, based on different physical quantities, but the mutual inductance is still the same in both cases. So now I would like to make an illustration using a simple example. This example also shows that we have one kind of problems with magnetic field which is very important. In fact, some 15 years ago, banks have switched from having signatures on sheets of paper. In that case, you must be coming to your office. It was the same bank, but you could not go to another office, to another branch of the bank, because they had not this sheet of paper with your signature. So you had only one place where you can come with your orders, and they just asked you to sign the order. Then they brought the paper, compared it, and said, okay, it seems that this is the gentleman who signed it, who has the right to sign it, and they carried out the order. Then what they have done, they scanned it. At this moment, any branch could see your signature, and at this moment they could carry the order. But there was a problem. Within the black market, criminals have a price that was not very high, traded a device that was capable of reading the content of the screen at a distance of 40 meters. It was a kind of Yagi antenna that has been pointed to the screen, so they could come with a lorry, hide the antenna on it, and they could read those computer screens. And that was a problem which then should have been addressed by banks. And this is one of the points where coaxial cable, for example, is important, because it does not leak the information if properly designed. Now, that was a short introduction, but the important point is the information that is transferred by any current leaks out, and all the authorities have to take care not to have this leakage detectable outside. So there is a number of leakage-proof rooms in which important information in computer form is stored. And second, of course, there is a lot of encryption. That's the second step provided by information theory. But the leakage of information from conductors is a problem. And my next illustrative example is more or less doing this topic. So let us have a straight conductor carrying a current I. The question is whether there is any inductance in the case when we place a loop, a rectangular loop, on the same plane as the conductor. So in some distance from the conductor, we would have a loop. The loop, of course, is not short circuit, it's an open loop connected to some detection device for detecting the information here. But anyway, we are now not concerned about data leakage. We just want to establish the value of the mutual inductance between the wire and that rectangular loop. In order to be able to do that, we would have to add some dimensions on the picture. So first, this distance would be small a. Now, this distance of the loop would be small b. Now, this dimension of the loop is C. We have the current I, and now we have everything we need for the calculation, provided that we consider that both the loop and the wire are positioned in open air, so that the permeability of the media is mu0. So we know the permeability, we know the arrangement, and now let's find out how to establish the inductance, the mutual inductance. So we would have to find out the flux flowing through this rectangle if there is current I in this wire. We know a formula based on the Ampere's law, which tells us exactly the value of the magnetic field around the conductor, bearing in mind that B is in linear isotropic media mu h, and that is mu times I over 2 pi r, just refer to our last lecture. We have the flux density. As we can note, it depends on the distance. So if we have the distance from the y, which is r, we would have different flux densities at different locations. At this point, we cannot simply multiply some value of flux density with the surface of the coil. We would have to carry out integration to get proper results. So what is the flux flowing through that rectangle? Well, let's get a small differential piece of that, in which the value of flux density would be constant. That means it must have the same distance from the current that causes the flux. So this small piece, small rectangle, let's say, with the differential thickness dr, would have the benefit that the field inside it is constant, so that we can find out the flux through this small rectangle just by its radius r, the distance from the conductor bearing current, and the width and depth. So it's quite simple. The element of the flux, d phi here, would be B, given by this equation, multiplied by dr and multiplied by c. That's the surface of that differential rectangle. So we would have mu I over 2 pi r multiplied by c and dr. That's the element of the flux. Now it's quite simple to get the total flux by integrating this element from this end of the loop, to A and B, which is the other end of the loop. So let's do that. The total flux phi is an integral from A to A plus B, and the integrand is mu I over 2 pi r multiplied by c dr. As you can see, most of the expression in the integrand is constant, so we have mu I and 2 pi and c that are constants that do not depend on the radius r. We can put them again out of the integral, and the only thing that remains there is 1 over dr, which is a simple integral of the form logarithm of r. Now we can again put there the upper bound, a plus b, and the lower bound, and we would get a result. Let's write it down. It is mu I over 2 pi c multiplied by logarithm of, and the logarithm is taken out from a plus b over a. So now we have got the full expression for the flux that flows through the loop caused by the current in the conductor. Well, we have got the flux. Our original question was not flux but inductance. So let's get to the inductance that we achieve by dividing the flux by the current that causes it, and therefore the mutual inductance in between a straight wire and a rectangular loop positioned in the same plane as the wire becomes mu c over 2 pi natural logarithm of a plus b over a. Now a comment. In the case that you can position your reading device, your loop, in a distance from the wire that is comparable to the loop width, so if B is comparable to A, you will get something like a logarithm of 2. That's a number more or less 1 in the result, slightly less than 1 or around 1, or slightly more than 1, but more or less the order is 1 unity. And now you get the rest of the equation. The important point is that mu is the permeability, in this case the permeability of the air, which is 4 pi raised to 10 multiplied by 10 raised to minus 7 Henry per meter. So more or less you have something like microhenries. Well, microhenry is a very small inductance, but you can do, if you want to listen, you can do one thing, and that is to add more turns to this device. So if you, for example, would put there 1000 loops, you get somewhere to millihenries, and that would, in the case of 1 kilohertz in this wire, go somewhere to millivolts, and that's something that you can easily detect by a very simple electronic device. So the important point is that if you have an information transmitted using a single wire, you could easily get to very big problems with interference and especially non-friendly listening. What can you do against that? Well, the first idea, important for example even for your measurements, is that if there is some way to the load and a way back from the load, and there are two conductors, the simplest way is just to twist them together. Then the current going there and back would be very close to each other, and their field would mostly cancel. It will not totally cancel, but it would mostly cancel. So the first good idea is to twist any pair of wires that carry the information there and back. The second step could be using a coaxial cable. The third step would be shielding by some ferromagnetic or ferrimagnetics. The only real solution to the problem is not to use electric current at all. So far, communications carried out through optical fibers are not detectable. So if you really need something that is very private, you should use first very strong encryption, and second, not use electric current. Well, anyway, I have carried out one example of establishing a mutual inductance, and I would like to hear your questions. Okay, we have the right for a short break, second break in this lecture. So see you in 5 minutes again, and the questions, the paper will be still open for questions.